Hello students of ME352. This is let me see now, let me choose a nice pen here. Let's see, this can be here, ME352. This is in the form of reading notes for you. It's a video which I will put up. Our textbook is by Ghosh and Mallik, as I have sent you email, third edition, and this is from chapter 1. So this video will be called GM1a to indicate Ghosh, Mallik, chapter 1 and the first video. I will make more than one such video, and in this way all of those will be GM1a, GM1b and so on. So this book is Theory of Mechanisms and Machines. I would like to gently warn you that this course has a lot of geometry. And these days, the entrance exam de-emphasizes geometry. And so for many of you, this will have challenges. The geometrical methods will be many, and there will be difficult questions. For example, let me try a different color here. For example, suppose I have a hinge and a rod, and I have another hinge, another rod, then I have another hinge, then like this. Now, this is a stick figure, right? It may actually correspond, these lines mean it's fixed to ground. Now, this may actually correspond to something that looks like that, and this hinge is actually over here, connecting it to a wall that is over there. And this hinge is, of course, in the same place over here, but connecting it may be something more like that. And then over here, there may be something connecting like that, and then over here there may be something like this, right? So all of these physical dimensions that are not relevant to the main geometrical connections will often be de-emphasized in this course, not always but often, and we will be paying attention to the geometry. So for example, if I rotate this rod about this pivot point, this point will trace a circle, and then we are interested in questions like what is the largest angle through which this may rotate, or we may be interested in will it rotate the full way, or we may be interested in if we want the rotation of this to be related to the rotation of this in a certain way, then what should the geometrical parameters be. And as you can imagine, these questions are different from the sort of questions that you will encounter in other classes. The use of this subject is in the design and analysis, yes, of machines and mechanisms. What's a machine? The same thing is a machine when I specify loads and I pay attention to power and energy that are transmitted. Then it's a machine. Loads, power, energy. But if I am just interested in geometry of motion, which is a part of the whole study, right? But if I am interested in the geometry of motion only, then it is a mechanism. So to understand the geometry, we will be looking at the mechanism part. Okay, so that's the difference between a mechanism and a machine. Now, when we look at mechanisms, we have to pay attention to kinematic pairs. And a kinematic pair is a connection between two bodies, right? So the connection is called a kinematic pair, and they are classified according to the type of connection. So there are lower pairs, higher pairs, and there are wrapping pairs. At this point, I will stop and remind you that reading chapter 1 is your task. You must have the book. This video is only to accompany. It will help you read. I think if you try to read it, you will find that the book is difficult to read. There is a lot of material, and these notes in this video that I am preparing for you are to help you read the book. Read the book. You must read the book. Okay. So let's look at lower pairs. Lower pairs means there is an area of contact. Okay. So for example, if I have, let me draw a cross section so that it will be easier for you to understand. If I have I hope you understand what this picture is, but otherwise I will explain anyway. You see, this device is one, it cannot come out because of the end stops. It can rotate about this axis, right? So in a planar situation, what will happen is this kind of connection has a rotary single degree of freedom. This is a revolute pair. Okay, so when we indicate this connection, this is a revolute pair. This is a schematic. This is a different schematic. They represent the same thing. It is one kind of kinematic pair. It is one kind of lower pair. This is a revolute pair. It's a hinge. Okay, so that's one. We can have a prismatic pair. A prismatic pair is one where, let us say, let me draw a 3D version first. So here is, let us imagine that it is a square cross section. So this is like a square stick which is going into a square hole inside another bigger body. Continuing all the way through, this is the body here. This part, let me use a different color in fact to indicate what is going through. This is the part that is going through to the other side and sticking out of there. Okay, so this is one thing that is sliding through this hole of the same size and shape, so that it has only 1 degree of freedom like this. It cannot rotate. This is called a prismatic pair. This has 1 degree of freedom, which is rotation. This also has 1 degree of freedom, but it is translation. We can also have a screw pair. Let me come to that a little bit later. Let's do the cylindrical pair first. A cylindrical pair is one where this one would be round. So if this is round, going through, to the other side and sticking out round, then what happens is you can rotate it like this about its axis, and you can pull it in and out also. That's 2 degrees of freedom. That's a cylindrical pair. Now, if you have threads on this, so that per rotation there is a certain advance movement, then although both motions are involved, there is only 1 degree of freedom. That becomes a screw pair. Okay, so these are the lower pairs. There is also a spheric pair. A spheric pair is like this. Let me show you now. Where are we going? A spheric pair is, so spheric pair, this picture will not be very good. I'm sorry. I will show you a sketch first which is like a 3D section. Okay. So this is round and it fits inside a spherical cavity. And then what happens is this thing has 3 degrees of freedom. Spheric pair. See the book for a 3D picture. The idea being that this thing, if I just draw it with a stick figure like this for you to see, this thing can be rotated about this axis, it can be rotated about a perpendicular axis, and it can be rotated about this vertical axis also, about its axis, this axis. And so it has 3 degrees of freedom. That's a spheric pair. What else do we have? We have a planar pair. A planar pair is one where on top of some surface, I have something else. This thing has one translational degree of freedom, another translational degree of freedom, and a rotational degree of freedom. You can call it x, y, and theta if you like. This is a planar pair. Okay, so all of these are the lower pairs. Higher pairs have a point contact or a line contact. So higher pairs have a point contact or line contact. Point contact you will see in balls on surfaces, right? So this is just a schematic. It's a sphere on a surface, but you see this is what you will see in ball bearings. Line contact you will see in cams. So let me just draw one over here as we are starting off here. So you have a plate of finite thickness. Here you have a bearing. This is the axis. The cam may rotate like this. Now over there is a surface which this cam is touching. That there is a line contact there. There's a line contact. So these are higher pairs. Wrapping pairs are things like belts on pulleys. These are wrapping pairs. We will be mostly interested in these lower pairs and the higher pairs. Okay, so that takes care of the kinematic pairs. Now we will come to kinematic chains, links, and so on. So where are we? Let's come here and here. Kinematic chain. This is there in the book. You must read the book. A series of links connected by kinematic pairs. Then what is a link? A link is something, a link has two kinematic pairs, two or more, two or more kinematic pairs, then it is a link. Okay, a link that is connected to only one other link is a singular link. If it is connected to two other links, then it is a binary link, ternary link for three. These are things you will read in the book. If the kinematic chain series of links, so for example, like this, this, like this, like this, every link is connected to at least two other bodies, right? Then it is called a closed link. Every link is connected to at least two other links, L0, L1, L2, L3. L0 is connected to L1 and L3, and so on. This is a closed link. A lot of mechanisms have closed links, but there are open links where there is at least one link which is not connected to two other links. Okay, and the open link or the open chain is important in robotics. For example, you may have a base, some cylindrical thing that is mounted on that base. On that cylindrical thing, you may have a robot arm which has this axis, right? So you rotate about this and you rotate about this and you have an end effector over here. This is an example of an open chain. We may be doing more of closed, but open is important in robotics. Okay. Links can be planar or spatial. Sorry, not links. Mechanisms can be planar means all motion in parallel planes. Now, what does that mean? That means that, for example, I may have something like this. It actually has a finite thickness. On this, there is a pin. It's like this. I should erase this part. This time I will do it, but later I will request you to just imagine that it is erased. Okay. Now over here, this one is connected. Let me use yellow to indicate. Slightly easier for you to follow. There is another link which shares this common hinge. Okay. So the motion of this one is in a horizontal plane, and the motion of this one is in a different horizontal plane, but the motions of this and this are in parallel planes. In this also there may be thickness, there are different particles, but each particle moves in a plane and all those planes are parallel. Then it is a planar link, but you need not have just a planar link, right? So for example, that robot I had drawn earlier is spatial. There is a very important joint called Hooke's joint, which is spatial. You may have heard of this also as universal joint. So what happens is, if there is one shaft which rotates about some axis, and over here there is some other shaft which rotates about some other axis, how do you connect these? So you can have a semicircle like this with cross of some kind. I guess it will look like that. And then over here, this semicircle. So this semicircular part is attached to this. This semicircular part is attached to that. And there is a common plus shaped link here, like this. So this one rotates about this one and about those. And this is the Hooke's joint. In the book, in figure 1.7, it is slightly confusing because only quarter circles are shown. but this is the mechanism. Okay. Now, a constrained kinematic chain has a single degree of freedom, by which we mean that usually what we will do is we will fix one link and see relative motions. This is what we will usually do. Okay, so if I have this linkage, now the whole thing can fly through space. That's a different matter. You can throw it out of the window. But if we don't, if we fix this one, then we can still rotate this. And if we do, let me take a different color. If we do, this point will trace a circle about this center. And let us say from here it has come here. So now it is in this position. This point will trace a circle about this center. And when it has moved here, this will move enough so that this length is the same as that length, right? So this position is possible, and in this way I will be able to change this angle and new configurations will be generated. Don't be confused by the fact that there is another different configuration like this. That is not a local change, that is a big change. It is a globally different configuration. Over here, when I make a small change, there should be a small change allowed, and the structure should be possible to still assemble the structure in that way. Then you know that there is a degree of freedom. In this case, once I determine this angle change, the rest of the structure is determined. So this is a single degree of freedom mechanism, which, as the book points out, is called a constrained kinematic chain. Okay, good. We will do kinematic diagrams. Oh, by the way, if I had just 3, then it would not have any degrees of freedom. When I fix this, the whole thing is rigid. We need at least 4 links to have at least 1 degree of freedom. You will see later that it is possible to have more than 4 links and still have only 1 degree of freedom. That's not a big thing. So, for example, I can just show you right away. And this and this can be 1, in which case when I move this, the position of this is fixed, and the fact there are those links, the positions of those are also automatically fixed. This whole thing has only 1 degree of freedom. But the minimum number of links you need to have at least 1 degree of freedom is 4. Alright, now we will do kinematic diagrams. This we are talking about figure 1.1. Very important. So now we've come here and we are talking about figure 1.1 kinematic diagrams. Here what we do is we show only the essential features. So if something is fixed, held, fixed, we just show it like this. If one link and another are connected by a revolute joint, we show it like this. If one rigid body has an angle like this that is somehow important for us to show, then we will show it like this to indicate that it is filled in. You can think of it as a weld. If this continues and still has this fixed angle, then we will show it like this. Okay, see the book. If this one has a revolute joint with this one, then we may show it like this. Okay, if this one has a prismatic pair, so that means we can sketch it like this. We can say this is one body. See, this is one body, and then over here inside that slot is body 2. Body 2 slides like this. Then we may show it like this. We may show it like this to indicate that there is a slot and there is 2 in it. This will be 1, this will be 2. Pay attention now, important point. The length of the slot will usually not enter our calculations. It will not be that this sliding thing comes and hits the end. Okay, we indicate it like this with a finite length, but most of our analysis will be done assuming that this is long enough, the slot is long enough for this slider to for the slider to go wherever it needs to go for the rest of the motion to occur. And the final one, I have to move this one down just a bit. The final one is if I have, let us say, one body with one link here, another link here, another link here, and another link here, then we may reproduce this quadrilateral here, and we will have this link, this link, this link, this link. But to indicate that this is not 4 links but one, we may we will fill this one in with dots, or sometimes we may shade it to indicate that it is one body. Okay, so you can see now that this body is a link and it is connected to 4 other links, so it is a quaternary link. Yes, all right. Now there is a limiting situation that you want to see, and the limiting situation is like this. So let us say I have a 4-bar linkage, which I am now drawing like this. One here, another here, this one comes here. Now this point, you see, it moves in a circle. The motion of this linkage is the same as if I have the same here. I'm overwriting for you to see what is the same and what is not. But over here what I do is I put a slider, and then just beneath that slider I put a circular surface on which it slides. And you see, if the slider moves on the circular surface, then the motion of this hinge point is exactly the same as if this link was there. And then if this link, now let me use blue, if this link was longer, imagine that it's straight, then this would be closer to a, closer to a flat line. This would be closer to a horizontal line, and then this slider would be moving on something that is almost flat. And in this way, if it goes off to infinity, then this will be perfectly flat. And in this way, what happens is we can think of This is a slider. This is called a crank. In fact, I might as well say it here. This distance, this is an offset. And this one, I guess, that one, offset. So it's a slider crank mechanism with an offset. However, we may also represent it using a link like this. As shown in the book, it is shown with an arrow here and some dashed line like this to infinity. You will see that there are some situations where we will take sliders and think of them as equivalent to rotary joints attached to links of infinite length. You will see that. Okay. There is a small figure 1.14 which talks about disguise. It is easy. Please read it. I will not discuss it here. And now we will go to kinematic inversion. This is a really important topic. So we will go to kinematic inversion. Do it here. What is kinematic inversion? Kinematic inversion is a situation where instead of holding one link in a mechanism fixed, we hold a different one fixed and then we study the motion. So fix a different link and study the motion. You may think that it is obvious, but actually there are non-trivial consequences of this, as you will see. And when we fix a different link, what happens is that the relative motion stay the same. And that is the key part. That is the main reason why you do it. And so let us do a 4-bar mechanism first. Sorry. Let's see, is that? Let's do a 4-bar mechanism first. This fixed. So this one rocks. This one rocks. Okay. One structure, one mechanism. Same geometry. This one fixed is called a kinematic inversion of this mechanism, and the motion will look different. Okay, the motion will look different. In this case, you may think that there is not much difference, but let me give you an example where you will see that there is difference. Think about this mechanism where this link is of extremely small length. You will see a version of this later. This is an extreme case, easy to understand. This one, as you can imagine, will allow motions where this little link goes through 360 degrees. So for example, it may come a little bit like this, and this may come a little bit like this, and then it will be like that. So that is one configuration. You see, and then this will go. This is not an exact sketch, but believe me, you will see from further analysis that this happens. Now, then there will be a situation where this one has gone like that, this one has gone like that, and that intervening, this one, this little link has turned through 180 degrees. In this way, the little link can turn through 180 degrees, and these links are just gently rocking, while that one is going round and round. right? In a kinematic inversion where you fix this link, what will happen is that this will be a small one, this will be big, and this will be like this. And now you fixed this, and you can turn this with a motor. This will go round and round, and this will just be rocking gently. Its angle will be changing by small amounts. This one will not be moving. It does not look like this mechanism, but it is the same mechanism in the sense that this mechanism is obtained from this mechanism by kinematic inversion. Okay. Kinematic inversion gets more interesting or a little more interesting right away when we look at the following problem. So let's look at this problem now. Okay. So we are looking at this mechanism. All of this is there in your book. This video is only to help you read the book. When you try to read the book, you will realize that it is difficult. That is because the text describes figures, you have to go back and forth. That's the problem. This link is 1. Over here, this link is 2. This link here from here to here is 3. This sliding link is 4. Okay. Now, in the first version of this one, we are going to do kinematic inversion on this, right? So we have to fix one link. Suppose we fix link 1. In that case, we will have this situation. This is 1, that is 2, which we will call a crank. This is a connecting rod, that is 3. And this is a slider, that is 4. And this is 1 again, that is 4. This is called a slider crank mechanism. This is important in engines, right? So you know the engine cylinder is held fixed. The piston moves in the cylinder. There is a connecting rod and there is a crank. This one goes round and round. And then as this moves up and down, when you treat it as a machine, there are gas forces acting on it. And then this is going round and round. There'll be a flywheel and then gears and then other transmission, and then a vehicle may move, or you may turn a generator and generate electricity and so on. But in terms of just analyzing the motion, here, slider crank mechanism. Okay. Now, if you see the book, they talk about fixing 2, and when they fix 2, now it will be drawn like this. 2 is drawn like this. This one is now drawn at an angle because this angle keeps changing. This 4 is in there. This is 3, this is 1, this is 2, and you fixed this. Now this one is called a quick return mechanism. And why is it called a quick return mechanism will not be so obvious from here. But if you have seen a shaping machine in your manufacturing process class, then you may remember that a shaping machine has something like this. So it has, let us say, something long with a slot in it. Apologies for the poor drawing. Slot in it. One hinge here. And for ease of visibility only, I'll use a different color. So directly above this, another hinge here, a link here, and a slider here. Now, in reality, it may not even be a slider. In reality, there may be a roller there which has a small clearance, and then it sort of connects. But we will draw it kinematically like this. That is the motion. This roller has an extra degree of freedom going round and round, which does not affect other motion. So we are not studying that aspect here. Okay, let me erase it. Should use the hard eraser. Okay, let me use green. Now, here's the point. When I rotate this crank about this fixed pivot, it traces a circle. This is that circle. From here, I draw a tangent to the circle. This is that position. So, that is the extreme rightmost position for this rocking object. From here, I can draw another tangent to this circle, which sort of comes here. That is the extreme left position of that object. And then you will see over here, this arc subtends a smaller angle than that arc. So if that is the forward stroke, it takes longer to cover. The forward stroke takes longer. And then the return stroke is very quick. So it's really fast and it just comes back. That is why this is called a quick return mechanism. Now, how is this quick return mechanism the same as this mechanism here? Here, 2 is fixed, right? So I have 2 is fixed here. Let me take red. I come back here. This part here, red. This is 2 is fixed. This is 2 is fixed. The distance from this hinge point to this hinge point does not change. That is fixed. Link 1 is the rocking slider, right? So rocking thing with a slot, not slider. So here is the thing with the slot, which is rocking. It is hinged to 2. This is body 1. This is body 3. This one is 3. This, now I'm going to fill it in so that you can see it better. This filled in solid part with the hinge there. The hinge I will draw with blue so that you can see it clearly. Okay, so this part here, this part here, 4. So you see, that is the quick return mechanism. There is similarly an oscillating cylinder mechanism, which is not difficult, and I want you to read the book, so you please see that. And now I will do the fourth inversion, which is the water pump or hand pump mechanism. And the hand pump mechanism works like this. How does this work? In the hand pump mechanism, we fix 4. Okay, so we will fix 4. Let me use something greenish, lightish over here. So 4. Now remember that between 4 and 1, there is only this motion with no rotation. So now 4 will be shown like this. This is 4. It is attached to ground. This is 4. Okay. 1 slides relative to 4. So now 1 will be shown like this. What's the difference? 4 is connected to 3 and there is a hinge between 4 and 3, but 1 is extended by a rod which does not have a degree of freedom, rotary degree of freedom here. So this 1 is connected to a rod which is welded here and it has a hinge there. Okay. 4 is connected to 3 through a hinge. That hinge we will draw here. This is link 3. This also is link 1. This is 4. Between 3 and 1 with a revolute joint at both ends is 2. That is 2. I will draw it slightly bent. This is 2. What is interesting is that 2 will be extended. And now there may be some additional detail over here which will help you identify that it is a hand pump. Water will be here, it will come up, there'll be some kind of valve arrangement here, which we have not drawn. This is what you will be moving, and this will be going up and down, and water will be falling from here. That's the hand pump. I have seen this when I was a young boy. Many of you may have seen it. In the cities, it is a little harder because the groundwater needs to be close by, but some of you may have seen it. So from the same mechanism, we have the hand pump mechanism. So that is kinematic inversion. Now let's do one final example of such a mechanism, of a different mechanism, and kinematic inversions. So here we have this mechanism, which figure 1.21. So we have something like this. I will not even draw the whole thing. This part slides on that, and on it over here attached. So this whole thing, let me mark it like this. This part and this part all joined together, right? It's one body. And then we come here. Inside this there is a slot, one body here. And then over here is a slider. And that slider is connected by a link to ground. This is 1. This is also 1. This is link 2. I may be rotating it here. This slider is 3. 3 sits in body 4. So this also is body 4. Okay, so body 4 can only move like this. Relative to body 4, 3 can only move like this. Relative to 3, 2 can only move by rotation. Relative to 1, also 2 can only move by rotation. And the rotation of 2 causes sliding of 3, and the sliding of 3 causes movement of 4. You look at this, this is an abstract mechanism. It is not clear to you what its utility is. All right? But now, one thing you can see is that if this angle is theta, then this displacement, and if this length is L, then relative to this distance is L sine theta. So if you rotate this at a constant angular velocity, then this one will have a purely sinusoidal motion. Okay, this is not the same as a slider crank mechanism where it will be approximately sinusoidal. This one is exactly sinusoidal. Okay, now here's the point. How is it related to the slider crank? Let me show you. So over here is the crank, and over here is a slider. So this angle changes a lot, you see. This angle also changes. This angle also changes. Okay, so if this is L1 and this is L2 and this is theta and this is phi, there is only 1 degree of freedom. Theta determines phi. So phi is known in terms of theta. Let me write phi of theta to indicate that phi is known in terms of theta. This distance is equal to L1 cos theta plus L2 cos phi of theta. Okay, so it is no longer purely sinusoidal because phi depends in a complex way. But now, if I make this longer, then phi is closer to 0. So this is just closer to a constant, and I make it still longer. and so on. So as L2 goes to infinity, what happens is that this becomes a relative to the other one. There is a vertical slider. That is the vertical slider you are seeing here. So inside these abstractions and drawings, there are things for you to think about. So this is really like a limiting case of a slider crank mechanism where the connecting rod has gone to infinity. Then from that infinity, you've brought it back, but you've kept it here as a sliding joint as opposed to a rotary joint or a link of finite length. Okay, so this one is called a Scotch yoke, I believe, and Scotch yoke. But there are other mechanisms. Okay, so other kinematic inversions of this mechanism. You should read the book, of course. This is not a substitute for the book. It is only a reading aid, right? So after you watch this lecture, if you read the book, you may find it a little more easy to understand. So the other one is called Oldham's coupling, and it is actually very clever. So in Oldham's coupling, what happens is link 2 is held fixed. Okay, so if link 2 is held fixed. Now, if Oldham's coupling is drawn in your book in figure 123, how does it work? So Oldham's coupling is like this. I have a disc with a slot. This goes through, and then I have a rotary degree of freedom. Okay, so that's the disc with a slot. All right. Then I have another connecting disc, and this is the clever part. I have another connecting disc which has a perpendicular sort of key sticking out of it. Then, so you can see that key. Look at the picture in your book for greater clarity. And you come here, and there is this other key sticking out like this. Okay. So let me clarify. Let me use this eraser to make it a bit better. Let me first indicate that the edge of the disc is this. That's the side edge of the disc. And then using pink, let me indicate this one is a key. It is horizontal in the present configuration. Of course, everything will rotate. And this is another key that is vertical. This horizontal key fits in this horizontal key. When it rotates, this disc rotates along with it. Okay. Now over here, okay, so this vertical key sits in this vertical slot here, and this one rotates. I am very sorry for my bad drawing. I have to change this. Please excuse me. Um, Let me go back here and try to repair the damage. This axis and this axis have to be parallel. Okay. However, they are not coincidental. So it is like here is one shaft, here is one shaft. This one is rotating, this one is rotating. How do you transmit rotation from year to year? By allowing an arbitrary amount of offset. That is what this mechanism does. And the way it works is you can see that when this one rotates, this one slides over here as it wishes, and then it slides here as it wishes to accommodate the location of that slot and this slot. But whatever is the angle of this slot, that is the angle of this key, that fixes the angle of this key, and whatever is the angle of this key, that is the angle of this slot. And therefore you see whatever is the rotation here, same is the rotation here. This is how Oldham's coupling works. Now what is being held constant or held fixed is link 2. That is what we are told. Link 2 is connected Link 2 is connected through rotary joints to 1 and 3. Okay. Link 2 is connected through rotary joints to 1 and 3. Let us go there. Link 2 is connected to rotary joint through rotary joints. I will make a mistake. This has to be 1. Link 2 is fixed. It is connected through a rotary joint. So this, let us use yellow. Let me say this is 1. And link 2 is connected here through a rotary joint to this one. Let me say this is 3. Okay. 1 and 3 are connected rotary joints. Then I come back here and you see that 3 is connected to 4 with a prismatic joint and 1 is also connected to 4 with a prismatic joint. So I come back here and I see 3 is connected to 4 with a prismatic joint and 1 is also connected to 4 with a prismatic joint. This is body 4. And so this is the physical construction. Even this is idealized. You'll wonder about friction and things like that. We are not worrying about those things here. Imagine it is perfectly lubricated, whatever it is. Don't worry about that. We are studying the motion. That is hard enough. But over here you can see that there is this body, this mechanism, this Oldham's coupling is a kinematic inversion, obtained by a kinematic inversion of the Scotch yoke. Okay, and there is a third one which is called the elliptic trammel. We will do that also and stop this lecture. So here we are, elliptic trammel. What this one has is, I'm going to look at the picture, figure 125, and I'm just going to take a bit of a shortcut and indicate the midline of one slot here and the midline of another slot here. Then I will draw this slider here and I will draw another slider here and I will put a hinge here and a hinge here, and what I will do is I will connect this with a line that continues like that. And maybe this is my point of interest. This point is D. It's point of interest. Point A is here. This point is A. This point is B. Okay. This one moves in this slot. This one moves in this slot. The question is, what is the motion of D? But first, let us try to understand. This one is now body 3. Okay. What is it? 4. It's 4. Okay. It's 4. This one is body 4. This one is body 4. Body 4 is fixed in this kinematic inversion. Remember here, body 4 was sliding, 1 was fixed. Okay. Now body 4 is fixed and body 4 has 2 sliding joints, one with 1 and one with 3. And 1 and 3 are connected by a link through revolute joints. Come here, right? So here I have body 4. This also is 4. This one, let us say is 1. This one, let us say is 3. So 4 is connected to 3 through a sliding joint. 4 is connected to 1 through a sliding joint. 1 and 3 are connected through body 2. This here is body 2, revolute joint. and we have extended body too, just like in the hand pump mechanism we had extended, and we are interested in this location of this body D. Now what happens is, let us call this the x-axis, let us call this the y-axis. What is the coordinate of D? Well, the x coordinate of D is AD times the sine of this angle. Let us say this angle is theta. Okay, so x is equal to AD sine theta. Y is equal to BD cos theta. This means x by AD square plus y by BD square equals 1. That's the equation of an ellipse. And therefore, this point will trace an ellipse. Okay. If AD is equal to BD, then it will be a circle. For AD to be equal to BD, D has to be at the midpoint here. Okay. All right. That's the end of this lecture. Thank you for your attention.